So the question is, explain exponential decay and detail and outline the important features of an exponential gap. So the way you answer this question, the first thing is you do the equation. So y equals b a to the negative k x, and the reason why it's negative x because it's declining. So example, exponential decay. A to the e, Euler's numbers. Y is natural logarithm decay. Important in first order kinetics. Elimination kinetics from the plasma. Alveolar inflation, radioactive decay. So these are examples. And then you talk about single compartment, C equals CO, e to the negative KT. Single doses are given in the compartment, which equals VD. C is plasma concentration, CO is drug concentration at time 0, T is the time, K is the elimination rate. And then K is clearance over VD. K is also 1 over T. So there's a lot of equations here, but I think this is all you need, and the K is 1 over T. Then you draw it and you show that it's negative exponential. The important factors are the horizontal asymptote. So once you draw it, you can kind of remember the stuff. So horizontal asymptote, which means that it theoretically doesn't actually reach zero, but it looks like zero. Constant proportion of decay, so the half-life is T half ln 2 over K. The slope, so the K, which is the integration of that over that, gives you the slope, okay? And that's a constant time. So the horizontal asymptote is reaching zero, and then you talk about the constant proportion of half-life, which is T half over ln 2. Now the instantaneous proportion, this is where it gets confusing, right? So we know that if you want to get a gradient for anything, you differentiate it. When you differentiate, you get negative KCO e negative KT. But if you want the constant, the equilibration, the elimination constant, what you do is what? You divide C dash over C, and that gives you negative K. So you increase concentration, you increase the amount of drug. However, it's the same proportion. And then that ties in with time constant. So time constant is the time for an exponential to reach 63% of decay. All the time required to complete the decay function had the initial rate of decay continued. And that's tar, not T, tar is 1 over K, or 1 over EX. After X number, time constant. After 1 time constant, Fx is 1 over e to the 1, that's 37%. After 5 constant, it's 1 over e to the 5. So that's just the time constant, which is obviously related to 1 over the K, or 1 over e to the X. So that's just because it's an Euler's number. I don't know, just memorize the crap out of it. So time constant is an exponential function to reach 63% decay, or the time required to complete the decay function had the initial rate of decay continued. And tau is 1 over k. So I guess you can't really say that these, but just say that tau is ln 2 over k, and then this is 1 time constant, this is 2 time constant, and so on.